In the second part of chapter 14, we're still talking about regression, but we're going to talk about multivariate regression. So multivariate regression allows the analyst to present several variables in one equation. And by several variables, we mean several independent variables. We're still trying to predict one y variable, but we're using more than one independent variable. You still have a constant, and then you have n, however many that might be, independent variables and one dependent variable. Each regression coefficient b sub I, so if you notice here b1, b2, etc., is what's called a partial regression coefficient, indicating the effect of that independent variable on the dependent variable y while controlling for all of the other variables in the equation. There's an example in your book about data collected on selected employee characteristics from a sample of the federal government personnel records, and they wanted to derive a regression equation to explain a person's grade level of entry into the federal career service. And here are the regression coefficients that they obtained when they did this regression analysis. And you notice they have a very large number of variables in the equation. It included things like years of education, potential experience, veterans preference, and the veterans preference was a bonus that was added to the scores, 5 or 10 bonus points. The remaining variables are what we call dichotomous or dummy variables. A person who has a characteristic or does not have the characteristic. So for instance, on the variable female, white female, if the person is a white female, they were coded 1, otherwise they were coded 0. Female and minority appear to have little effect. So if you look at the coefficients here, they're not really doing much in the equation. Education has a positive effect, and if we look at the years of education here beyond high school, and engineering and math, business, here's your biology, which has even a bigger effect. The biggest effect of all is a law degree. Coefficients for minority and female status controlled for years of education, but they reduce the overall grade level. By reducing it, we mean they have a negative coefficient. So now let's use the equation to do some predictions. So what grade level would you predict for a white male, law school graduate, no veterans preference, 26 when he finished school and he's now 28? The definition of potential experience is the difference between school finishing age and entry level age. So he would have 2 for that particular variable. And so what we can do is take the values for this particular candidate and substitute them into the equation, and then go ahead and calculate the 0 values. Remember, for the dichotomous, he doesn't meet those criteria. His overall grade level is predicted to be a 10.63. What grade level would you predict for an African American female with a master's degree in biology, no veterans preference, 24 when she finished school, and now she's 25. So again, she's got one potential experience year. And then again, if we substitute into that formula that we had from the multiple regression, we get 6.27 as her predicted grade level. The regression equation predicts the average entry grade level for people in the population, persons with records in the sampled files. The data set excluded people who applied but were turned down or were never selected for an interview. And also the data set does not include people who never applied for a federal position. So although gender and minority status did not appear to affect the predicted grade level, the variables are kept in the equation to demonstrate their lack of effect. Someone could criticize you if you didn't include those variables by saying, well, you've overlooked something that might have a significant impact. By including them, even though they don't appear to be affecting the grade level, we show that we did consider those. So the coefficient of multiple determination for the multiple regression equation is also called R squared, and it indicates again the degree of variation in the dependent variable that's explained by the model. In the example that we just went over, it was 69%. We can continue to add variables, and the R squared will remain the same or increase. It will never decrease. Generally, 5 or more variables will explain much of the variation in the data set. And you can have more independent variables than observations in your data set. We can adjust the R squared by penalizing every time we add another independent variable. Adjusted R squared cannot be larger than the original R squared. Here's the formula for calculating it. When to stop adding variables. You should include variables that are important to the model, but you also want to consider how the R squared is being affected. Simply seeking the highest value for R squared is not recommended. Some researchers exclude any independent variable whose coefficient, that is regression coefficient, is not statistically significant. So from our example, we cannot rank independent variables in the order of their contribution in explaining the dependent variable. Regression coefficients are affected by how we are measuring the variables. So for instance, years of education went from 0 to 10 for beyond high school, and the coefficient was 0.5. So the largest impact here would be to add 5 to the predicted score, or predicted grade rather. The life science was a dummy variable. It was coded 1 if they had a life science degree, which means if they did, that would add 0.97 to the predicted grade level. We can standardize the regression coefficients, and these are called beta weights. And what this allows us to do is easily and precisely compare the relative importance of each variable because it removes the effect of the units. We normalize by rescaling each variable so the mean is 0 and the standard deviation is 1, and then the larger the beta weight, the stronger that variable's relationship is to the dependent variable. So let's take a look at an example. Admission criteria. Analysts developed a 12-point scale to summarize personnel qualifications such as previous work experience, evidence of undergraduate leadership. They calculated scale scores for admitted students and then computed the regression equation to see if the scale would improve the quality of the admission decisions. And the graduate school performance was the dependent variable. 2 equations were developed: performance during the entire graduate program and then also performance during the first semester. So if we take a look at what we got, this was predicting the grade point average. And if you notice here, these are the unstandardized regression coefficients, and these are the standardized ones. And if you notice the beta weights, the undergraduate average is the most important, especially when we look here in the standardized where they're all on the same scale. The most striking is the importance of the GMAT, which really had a very small coefficient here, but when we standardize it, it now is the second most important, or tied for second place in terms of the most important when we look at the beta weights. Examining the t ratios, the rule of thumb is any ratio greater than 10 will be significant. And in this particular example, if you look at calculate the t's there, undergraduate, GMAT, and admission scales, the first 3, would have a significant t statistic. And if we look at the R squared, now this is interesting. Start out with just the undergraduate average, and we're at R squared of about a little bit more than 10%. If we add the GMAT, we go up to about almost 15%. And then if we add that admission scale, we go up to 18%. But now adding additional variables here is not really gaining very much for us. So it appears that the 3 variables that had the significant t statistics also give us the most consistent R squared. Adding additional variables does not really dramatically increase the R squared. And if you think about trying to collect the data, having to only collect 3 variables would be less time consuming than collecting more variables. So 18% of the variation in the first year grades was explained by the undergraduate average, the GMAT, and the admission scale. 82%, however, of the variation in the first semester grades is not explained by this model. And so perhaps there's some other variables that we haven't included that would really help improve that model beyond the ones we did look at. So tests of statistical significance. The t ratio is used to determine if a particular regression coefficient varies from 0. We can also do an F ratio, which is looking at the explained to the unexplained variance, and it's testing the entire model. It's looking at all the partial regression coefficients and saying, is there at least one that's not equal to 0? And the test statistic that we use for that is called an F test. And here's the calculations that we use for that. So example 3, investigator wants to identify management report characteristics associated with their actual usage. And he measured these variables. Y is what we're trying to predict, which is the average frequency the manager discussed the report information with others. And then the independent variables were the frequency of the report, the medium, whether it was printed or produced online, the quality of the report, the accessibility of the report information, the perceived value of the report. The strategy, evaluate alternative exploratory models using multiple regression. So here's actually 3 equations. And if we look at the first equation, it's got an R squared of 10%, and it included the first 2 variables, which if you remember were the frequency and the medium. So whether or not it was, so if it was online, actually that led to a decrease in the average frequency. Equation 2 now added 2 additional variables, which was X3, which was the technical quality of the report, and also X5, which was the accessibility. The beta weights changed. Now these are all beta weights here. So the beta weights on the initial variables changed a little bit. And we notice we still have significance here. And actually X5 is also significant. and is having a coefficient in the same range as the other two variables here. And then equation 3 adds yet another variable, which actually is significant, interestingly enough, which is x4, the accessibility. But the r squared hasn't changed. And so when you take a look at this, it looks like equation 2 is the best equation because it's giving us the largest r squared and yet including only 4 variables. And again, the overall f-test was significant, which tells us at least one of these coefficients is not equal to 0. So beta weights show the report frequency is the most strongly related to the frequency of use. The perceived value of the report and the medium are also strongly related. And notice that we looked at those footnotes for the p-values. The technical quality may not be associated with the frequency of use. And the F ratio is highly significant. There's a low probability any of those relationships happen by chance. Last topic in this section is called multilinearity. And multilinearity occurs when we have highly related independent variables are used in a model. When two variables are highly correlated, the regression equation can't accurately estimate their independent effects on the dependent variable. Here are some of the symptoms. The multiple regression equation is significant, but none of the t-ratios are significant. The addition of an independent variable radically changes the values of the beta weights or the regression coefficients. So what can you do? The first thing suggested is to look at the correlation matrix for all the independent variables. And if you see a correlation, absolute value of it greater than 0.8, it suggests multilinearity. In which case you might want to consider removing one of those two variables that are showing that high correlation. Consider a problem of sampling. The type of selected cases don't allow estimates of each independent effect. Gathering additional cases might help. Sometimes we can modify the model. Again, variables may be combined into a single measure. Multilinearity is really saying that the two variables that are highly correlated may be actually measuring the same quantity. It may not be a concern if the purpose of it is forecasting, where the accuracy of prediction is most important and the coefficients is not as important. So you have to think about that in your particular situation. So this week again we're continuing with regression, and we covered multivariate regression and topics related with that, predictions, and then also the multilinearity.